So hello and welcome back. So in this video I want to show you how to do logarithmic scale, and the reason why I need to do that is that, as you saw in the previous video, we had some data over here. So we had all of this business of we had the frequency over here that goes from 10 hertz all the way up to 10 megahertz. Okay, so you're multiplying by a factor of 10, 20, 10, 1, 2, 2, 3, 4, 5, 6, 10 raised to the power 6, meaning that you're multiplying by a factor of 1 million to get from here all the way up to here, right? So you go all the way from 10 hertz to 10 megahertz. You're multiplying by a factor of 10 raised to the power 5, 10 raised to the power 6. So what basically what you want to do, what usually when you have your data lined up like this, so here was basically some input voltage that we measured on the signal generator, and then there was some output voltage that we measured, and now what we want to do is that we want to do a graph of something like this, meaning that we want to do a graph of V of out, which is basically this output voltage over here versus frequency versus f of in, frequency, input frequency, and you would get some, for example, some function like this or something like that probably. But now the problem is that, well, the voltage that I have over here, the voltage goes from 28 all the way up to 2 volts, and then back to 10, 11 volts, and then goes down to 0.5, 1 point. So basically you want your voltage from somewhere from 0.5 to 28 volts, somewhere from 0.5 to, for example, somewhere over here, which is 28 volts. This is in volts peak to peak. Okay, so it's not hard to basically to plot these points on the vertical axis, meaning that, for example, you can take this as 2, for example, 2, 4, 6, 8, 10, or probably, for example, 4, 8, 12, for example, 16, 20, and so on and so forth, and somehow you can get to 28 volts, meaning that you can make this vertical axis a little bit longer, probably few centimeters longer, and you get to 28 volts, and you will still have enough space between, for example, between 4 and 8. You will have enough space if you were to, like, for example, find some voltage like 5 volts, 6 volts, 7 volts, and so on and so forth. So on the vertical axis you have no problem, but on the horizontal axis you see that your frequency starts at, for example, 10 hertz, and here you go all the way up to 10 million hertz. Over here, let's say that this is the end of your range of frequency, and here you're at 10 million hertz, which is basically 10 megahertz. So now there is really no good way to do this, meaning that I can, for example, I can say that, okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, for example. Okay, and forget about this whole thing over here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. and I call this 10 megahertz, and then based on that this would be 9 megahertz, this would be 8 this would be 8 megahertz, this would be 7, 6, 5, 4, 3, 2, and 1 megahertz. This is 1 megahertz. And well, of course I could start from 0 megahertz, for example. I could say that this is 0, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 megahertz, and then that's basically, but then each division over here becomes 1 megahertz, and 1 megahertz is actually 10 raised to the power 6 hertz. It's 1 million hertz. So then if I were to find some point between 0 and 1, then I would have to mentally or on paper divide this very short distance into 1 million pieces in order to find, for example, I don't know, 253 megahertz. I'm sorry, 253 kilohertz or so. So then it's just not possible. So in such situations, what we do is that we still use a I mean, wherever it fits, we use the same linear scale on the vertical axis for the voltage, meaning that I say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and 22, 24, 26, 20, probably 28 if I haven't made any mistakes in counting, but that doesn't matter. So each of these is basically 2 volts peak to peak. Okay, so I have no problem here. And this thing over here is a linear scale. This thing over here is a linear scale, and then on the horizontal scale, you have to, in order to get around this problem of basically having to divide each, for example, having to divide 1 centimeter into, for example, 1 million equal distances, which is next to impossible, which is of course impossible. And what you do is that you start at, for example, you start at you start at 1 hertz here, for example, and then you have these distances over here, okay, the same equal distances. And then when you move to the next basically to the next division over here, you multiply by 10, meaning that this is 10 hertz. Again, you multiply by 10, so you get to 100 hertz. Multiply by 10, you get to 1000 hertz. So this is 1 kilohertz. Okay, and then again you multiply by 10, and then you get to 10 kilohertz. You get to 10 kilohertz. Multiply by 10, you get to basically 100 kilohertz. You multiply by 10, you get to 1000 kilohertz, which is 1 megahertz. 1000 kilohertz, which is 1 megahertz. And then here again, if you multiply by 10, you get to basically 10 megahertz. 10 megahertz. And that's basically the end of the range that we are looking for. And that's basically what that's basically, and that way you will be able to have all the possible values from 1 hertz all the way to 10 megahertz on this very short scale, meaning and probably on 6, 7, 8 or 10 centimeters length, you will be able to have all the way up to 10 megahertz. So and then it's also very easy to basically to move around on this scale if you use logarithms, and this scale is basically called a logarithmic scale. Okay, now the way that you can move on this scale is a little bit different than how you move on a linear scale, and I'm going to show you what I mean by that. So let's say that you have, I don't know where my, of these two, I don't want to lose my data. Okay, so let's say that you have a linear scale. So on a linear scale, what you do is basically you have this number line over here that you use as a scale, and then you start, for example, somewhere at 0, and then you usually, for example, you define some sort of fixed distance on the number line. For example, you say that this distance over here is 1 unit. Okay, so then that means that this distance, if you move this distance on this number line, that's going to be 1 unit. So if you move twice this distance on this number line, meaning that if you move twice this distance on this number line, so if I take this A as A, 2A is going to be 2 units. If you move thrice this distance, thrice A on this number line, it's going to be 3 units, meaning that if you move all the way up to here, it's going to be 3A, and then as a result you will get to positive 3, and then you do the same thing over here. That would be -1, that would be -2, and so on and so forth. And on this scale, when you want to find, for example, some number like 0.5, all that you have to do is, you know that 0.5 is half of 1 unit, so you have to move half of A. So then half of A is going to be this distance over here. This would be 1/2 of A, and so this would be 0.5. Or if you were to move, I don't know, if you were to find the number 0.8, it would be, for example, somewhere over here. So that would be 0.8 is 8/10 of 1 unit. So 8/10 of 1 unit would be 8/10 of A. If you move 8/10 of A over here, would be basically the distance over there, right, or the number over there. So that's basically what you do on a linear scale. So everything is basically based on this 1 unit, and then based on that you need to for fractions of a unit you kind of multiply it in this manner, and then you get to the number that you want on the number line. Now on a logarithmic scale, it's going to be a little bit different, meaning that if you have this, let's say you have this number line over here, and on this number line what you do is you don't start at 0. You do not start at 0, and for example you start at with a 1, for example, and then you say that this is a convention that you set based on the situation that you're in, and based on how your data is all scattered around and everything else. So you say that if I move this distance, for example, to the right, I'm going to multiply by a factor of 10. So then that gets me to a 10. Again, if I move the same distance to the right, So basically that would get me over here. Again, I have to multiply by 10, so 10 times 10 that gets me to 100. And the same thing basically keeps happening. So for example, excuse me. Okay, so we were talking about this logarithmic scale, and so we said that basically, for example, again, if you go this distance on the number line on your logarithmic scale, you have to multiply by 10. So for example, here you have 100, you multiply by 10, you get to 1,000, and that way you know where you are on the number line. On the other hand, so basically wherever you are on this number line, if you basically the important thing to know is that the important thing to know is your scale. Basically, if you call this your scale, for example, if you get from 1 to if you get from this distance, let's call this distance your scale, or your unit scale, for example. So your unit scale is multiplying by 10, and then it corresponds to this distance on this whole logarithmic scale. So at this point, if you want to know, for example, where 10 is, you have to go this distance, and this distance corresponds to multiplying by 10, and then that will get you to a 10. Or if you are at this point, for example, at this point 100, if you want to get back to a 10, of course you have to divide by a 10 to get to a 10, meaning that 100 divided by 10 is equal to 10. So that means that when you divide, you go in the opposite direction, and then the same distance the opposite direction. That means you're dividing by a 10, and that gets you from 100 to a 10 over here. So that's basically how you get around on this number line. Now, one thing which is different which is basically different between the two number lines is that since this is a linear number line, the distances on this number line are kind of proportional, meaning that, for example, if this is 1, then this is 2, and then this is 3, and so we said that, for example, 2 is basically, if you think of this distance as 2, it's 2 times 1, or if this distance is 3, it's 3 times 1, and so on and so forth. So everything is kind of proportional, but that proportionality is, of course, it is here as well, but in a different way, meaning that for example, on this number line, when you want to locate, for example, you want to find, for example, where number 2 is. For example, let's say that this is in the case of the data that we have, this would be, for example, 1,000 hertz or 1 kilohertz. Now you want to plot some point at, for example, 2 kilohertz. So how do you find 2 kilohertz on this logarithmic scale? So here we said that if you basically multiply by a 10, you will get to 10 on this number line. So what that means is that if you multiply by a 2, you have to basically that would get you to a 2 from 1, meaning that if you're at 1, so it's always like this, meaning that, for example, if you're at 1 and you want to get to 2, you have to multiply by some number to get to the number that you want. Okay, so if you're at 1 and if you wanted to get to 2, your x is going to be equal to 2. Now this 2 corresponds to basically fraction of this unit over here. So we said that this unit was times 10. So then you have to know, basically you have to know what times 2 is on this number line. And in order to basically find out what that is, you need to use logarithms on this number line. Now over here, if you want to basically, let me see how I can explain this. Okay, so I think I found a good way to explain this. So over here you see that, for example, if you were at 1 and if you want to get to 10, you have to multiply by 10, and we defined that multiplying by 10 means basically this moving this distance, this fixed distance on this logarithmic scale. Now let's say that you are at and remember that, for example, to get from 1 to 10, you're multiplying by 10, or you're multiplying by 10 raised to the power 1. Now if you want to get from, for example, to get from 1 to 100, you have to multiply your 1 by basically by 100, which is equal to 100. So that gets you from 1 to 100, and 100 is 10 raised to the power 2. If you want to go from 1 to a 10, you have to multiply your 1 by a 10 to get to a 10, and that is basically 10 raised to the power 1. If you want to go from 1 to a 1000, for example, what you need to do is basically you take your 1 and multiply it by 1000 to get to 1000, and this 1000 over here is 10 raised to the power 3. And you see that these exponents over here corresponds to how many times you have to take this distance. You have to take this fixed distance to get to the next number, and the next number to the next power of 10, and the next power of 10, in order to get to your number. For example, if you're at 1, if you take that distance twice, that takes you to 100. If you're at 1, if you take that distance thrice, that gets you to 1000. If you're at 1, if you take that distance once, that gets you to a 10. And that's basically how the system works. Okay, so now by the same logic, if you're at 1, and if you want to get to a 2, for example, you have to multiply your 1 by some power of 10 to get to a 2, as we did over here. I mean, every time I wanted to move on this number line, I had to take my initial number multiplied by some factor of by some power of 10 to get to my destination. So now I'm at 1. I want to get to 2. So 1 is my initial position, 2 is my destination. I have to multiply my 1 by some power of 10 to get to my destination. So that what that means is that 10 raised to the power x is equal to 2. And so if you want to solve this, you have to use a logarithm. I mean the logarithmic functions. So now x here is equal to log base 10 of 2. If you calculate on your calculator log base 10, which is basically on most calculators it's just written as log, as the simple log function, or you have a log function that in which you can specify the base as well. But when the base is not specified, that means that the base is 10, right? So now if I calculate log of 2, which means that it is log base 10 of 2, it's going to give me 0.301. So this is equal to 0.301. So that is basically That is basically how many times I have to take this fixed distance in order to get to number 2, for example. And what that means is that it's about 3/10 of this fixed distance, because this is 0.3. So 3/10 of this fixed distance would be, so let's say that this is 5, and then let's say that this is 5, and then if this is halfway between them, 3/10 of the, so let's say that this is so 1, 2, 3, and 4, 1, 2, 3, 4, 5, and then 1, 2, 3, and 4. So this is 5/10. This is 5/10, and this is, for example, 4/10. This would be 3/10 of that fixed distance, right? So 3/10 of that fixed distance, that actually corresponds to a 2 over here. Okay. And then, for example, let's say that you want to get to the number 8, for example. The number 8 is going to be at, again, you can do the same calculation, or you can simply calculate log of 8, and that gives you the fraction of that fixed distance. So, for example, you're at 1, and you want to get to 8, for example. So you have to multiply your initial position by some factor, by some power of 10 to get to your destination. So that then 10 raised to the power x is equal to 8. So x is equal to log base 10 of 8, and that is log 8. So then log 8 is equal to 0.903. I take it as 0.9, and this would be 9/10 of that fixed distance, which corresponds to an 8. Okay. Or if you want to basically get to 6, for example, if you want to get to 6, you simply calculate log of 6, and it gives you 0.778. I take it as 0.8. 0.8 would be right over here. So this is 9, this is 8, 5, 6, 7, 8. So this would be the number. I forgot what I wanted to calculate. So did I want to do 7 or what? So let's say that you want to get to 8, so that is log 8. Log 8 is equal to 0.9, which is basically this number 8 over here. Now let's say that you want to get to, for example, I don't know, 6, for example. Now log 6, for example, is equal to 0.77, so I take it as 0.8, and that would be number 6. So that is 1. So 1, 2, 3, 4, 5, 6, 7, and 8, and this number would be the number 6, for example, over here. And if you want to, for example, let's say you want to get to 7, for example, this is 6 and this is 8. Okay. You want to get to the number 7, for example. You simply calculate log of 7, and it's going to give you 0.85. So 0.85 would be, so it's 5, 6, 7, 8, 5. So it would be halfway between them. That would be the number 7 over here. Okay. So that is basically how you move around on this number line. And what you can see here is that basically as you on this number line, things are not as proportional as they are on this number line. So you see that the distance between 0 and 1 is one complete unit. That you have the same distance between 1 and 2, the same distance between 2 and 3. But when it comes to this number line, when you move from 1 to 10, you see the distance between 1 and 2 is much larger than the distance between, for example, 6 and 7. This is the distance between 6 and 7, very tiny, teeny distance between them. But the distance between 1 and 2 is a large distance. So as you get farther away from these numbers, 1, 10, 100, and so on and so forth, the numbers will be kind of cramped together. But in the beginning, the distances are much larger. You can still accommodate much more numbers between these numbers in the beginning, and then in the end, as you get to the end of the spectrum, if I may call it, then things kind of get very, very cramped together. Okay, and let's say that, for example, you want to get to 20 over here. Okay, so to get from 20, I know where 10 is, so from 10 I can get to 20, right? So from 10, if I want to get to 20, I have to multiply 10 by some factor of 10 to get to 20. Okay, so that means that 10 raised to the power x is equal to 20 divided by 10, which is equal to 2. So 10 raised to power x is equal to 2. Now x is equal to log base 10 of 2. And if you calculate log of 2, and then go 3.3 units in that direction from 10, you will get to number 20, meaning that again you can basically divide distances into 10 equal distances. So 1, 2, 3, 4, 1, 2, 3, 4, and that would be 3/10 of a complete unit. So that would be, for example, number 20. So basically this would be, for example, this distance over here from 10 to 20. This would be, for example, times 2. And if you, for example, if you're at 20, and if you multiply by 2, you'll get to a 40, meaning that if you go with the same distance in the same direction over here, somewhere over here, that should give you, for example, the number 40 or so. But we can actually try this. So basically what I can do is that I can start at 10 and calculate how much I have to go in this direction to get to a 40. So I'm at 10 and I want to get to 40. So 10 raised to the power x is equal to 40 by 10, which is equal to 4. So x is equal to log base 10 of 4. Log base 10 of 4. Now log 4 is equal to 0.6. So 0.6 would be, so this is 10, this is 1, 2, 3, 4, 5, and 0.6 would be over here, and so it's not very far off. I actually, if I had taken the units proportionally, of course I would have gotten to the same number. And that's basically how you move on this number line. That's basically very simple once you get used to it, and then, but of course very useful, meaning that, for example, now I'll show you in the next video how you can actually use this logarithmic scale in order to basically, for example, plot some frequencies along the horizontal axis and basically do a graph on that axis. And usually when it comes to this kind of thing, you usually use graph paper. So you usually use your graph paper in a landscape orientation, and then do basically your units on this, and then you kind of need to know. I have never used graph paper or square paper like this. So we will do this graph together using the data that we have, in order to basically do the graph of the data that we had in the previous experiment that we did with that circuit. So I'll see you in the next video. Thank you.